Hey all dear students, this is Prajesh Chaudhary, your quantum guru. Let's see this very good question of Pathfinder from methods of impulse and momentum. So the question states two identical small balls A and B, each of mass m, connected by a light inextensible cord of length L, are placed on a frictionless horizontal floor. With what velocity u must the ball B be projected vertically upwards so that the ball A leaves the floor? Acceleration of free fall is g. Alright, so here is the picture. The floor is smooth, frictionless. At the initial moment, this is at rest, so the velocity of center mass is u by 2 in the upward direction. The forces acting on them as a system, the tension here, the tension T, for the whole system tension is internal. Other forces are the weight and normal, so they are in the vertical direction. So all the forces are in the vertical direction. Initial velocity of the center mass is in the vertically upward direction. Acceleration of the center mass is also in the vertical direction. So center of mass will move vertically upward. So this is the center mass. So center of mass will move along this line. Now let's take the moment. This is the moment when A lifts. So A lifts, so there are many ways to look. If you look from the center of mass of the system, that is the midpoint of the string, so the distance between midpoint and the either ball will not change, so path would appear to be circular. But in the ground frame, that point itself is moving, so from the ground frame this path of the B is not circular, so it would be something like that. So obviously till the moment the ball A is about to lift, the length, the cord has rotated, and we will treat this cord as a rigid body because there is no slacking involved. So the angle rotate is theta till that moment, and the center mass is moving like that. The A so far is moving till it has not lifted, it will obviously move along the floor. So the initial position of A was somewhere here, so it has moved here, and the B has moved something like that. So we will focus on A. This is the moment A is about to lift. So draw the FBD of A. There would be tension and the weight downward direction because it has just lifted. So it has lifted, so tension normal has become 0. So basically for normal to become 0, this component of tension is balancing mg. So this component of tension is what? T sin theta. So T sin theta is mg, so that is the at that moment when it lifts. Okay, and the center of mass has moved this way. So at the moment of lifting, the center mass has a velocity vcm, and this cord has from this orientation to this orientation, obviously it has rotated. The whole system has got some angular velocity like that. So there is some RBD concept also involved here. So with respect to center mass, if I see this length is L by 2, so with respect to center mass, A would have velocity omega L by 2 here, and the center mass has also velocity, so with respect to ground, the velocity of A would be vcm upward and omega L by 2 like that. This is, and the moment it has just lifted, the only force remaining, the tension is internal, cancel, the only force remaining is mg here. So ACM, acceleration of center mass, is F external upon total mass, so 2 mg by 2m, that is g. So the acceleration of the center of mass from this moment onwards would become g. Before that it would have been different, but now it has become g. Before that it would be less than g because there was some normal also. Okay, and now for the constant of this, so far the A was moving like that, and suddenly it cannot have a different velocity would be a continuous thing. So even at this moment it has a 0 velocity. After that it will get some velocity. If it has 0 velocity, when I say 0 velocity perpendicular to the surface, along this direction it has moved. So at this moment there is no velocity along normal to the surface, so this velocity and the component of this normal to the surface must balance. So VCM would be omega L by 2 cos theta. That is one more thing. And what are the forces acting on the system? The system so far before it has lifted, there was a normal here, and A was moving like that, so this normal was not doing any work, and the other forces, tension is internal, mg, so the forces are conservative forces, so its mechanical energy would be conserved. So from this moment till this moment, we will apply conservation of mechanical energy. Loss in kinetic energy is equal to gain in potential energy. Loss in kinetic energy is equal to K initial minus K final. K initial is simple thing. Final motion is, it is this length is rotating like that. This length is rotating like that, and it has a center mass velocity and it has some omega. So this motion is a CTRM, combined translation and rotational motion. In combined translation and rotational motion, the kinetic energy is equal to half m VCM square plus half ICM omega square. So now let me write the conservation of mechanical energy, apply conservation of mechanical energy. So loss in kinetic energy is equal to K initial minus K final. K initial is half mu square. K final for this thing is equal to half m VCM square plus half ICM square. Half m mean total mass, that is a 2m, and VCM square, half ICM omega square. And now the change in potential energy, this mass has not moved up, so this mass has moved from here to here in the upward direction like that. Basically it has moved like that, so vertical height changes this length. This is L and this is theta, so that would be L sine theta. So only B's potential energy has changed, so the change in potential of the whole system is mg L sine theta. And the moment of inertia of this whole system is equal to mu L square about this axis. So mu is equal to 2m upon m plus m, that is m by 2 L square. So put all this thing here. So half mu square, and that would be m VCM square. ICM is equal to ml square. ICM is equal to mu L square. Mu is m by 2, so that will be ml square by 4 omega square, and this thing, and just rearrange that thing. So after rearranging, we'll get this equation. We'll use that later. Okay, just this is the rearrangement thing. So here also I have expressed everything in terms of the omega and theta. I've used VCM is equal to L by 2 omega cos theta. So now we want to see the motion of B in the frame of center mass. So in the frame of center mass, the path is absolutely circular motion. The center mass frame is a non-inertial frame because center mass at the moment it has left, from the moment it lifts, it get the acceleration g downward. So center mass has the acceleration in the downward direction. So if I draw FBD of B in the frame of center mass, I will have also to apply the pseudo force. So two real forces are on M, that is one tension and mg, and this acceleration is g downward. So there will be a pseudo force mg upward. So its weight and pseudo force will balance, so only net force is T. So in C frame, B is moving in a circular path of radius L by 2 and only force is the T towards center. So directly we can apply equation of circular motion, T is equal to m by L omega square, m into L by 2 omega square. And from the motion, from the condition of lifting of A, we had got T sin theta is equal to mg. Just put here in place of this T, put ml by 2 omega square, so that would be this m cancel, and just rearrange that to get L square omega square is equal to 2gl sin theta. So all the physics part is done. Now we have to just correlate the previous equation and this. So in the last page we got this relation from the conservation of mechanical energy and velocity constant. So L omega square, put it here, and you check your own calculation, right? I have written previously, so that to save the time. So after that thing, we will get this relation. So u square is GL 2 cosec theta plus sine theta, and obviously this theta in turn will also depend on u. So how much this can take the value? So we'll use the maxima and minima. So for this part only, basically what is the, we want to put a limit on u. So that limit will be decided by this factor. So let's say f theta is equal to 2 cosec theta plus sine theta. For f theta, so f dash theta would be minus 2 cosec theta cot theta plus cos theta. For f theta to be okay, let's first just simplify that thing. This cosec theta cot theta is equal to cos theta by sine theta. Cosec theta is 1 by sine theta, so that is minus 2 cos theta by sine square theta. And f theta is minimum at f dash is equal to 0, f dash theta is equal to 0. So that whole thing here I have taken cos theta common, so minus 2 by sine square theta plus 1 is equal to 0. So this would be minimum when either this is 0 or this is 0. If this is 0, that would imply sine theta is equal to plus minus root 2, and this theta cos theta 0 would imply theta is equal to 90 degree. But is this possible? The modulus of sine theta is becoming greater than 1, so that is not possible. So this possibility is ruled out. So theta is 90 degree. So when theta is 90 degree, f dash theta is 0, so mean f theta is minimum. So from here we had got this u square GL. U square was GL 2 cosec theta plus sine theta. So u square is minimum at theta is equal to 90 degree. And if I put it here, so cosec 90 is 1, sine 90 is 1, so u square minimum is 3gl. So it means a u should be greater than root 3gl. U should be greater than equal to root 3gl, and that is what the velocity must be imparted so that B leaves. A leaves, sorry. Thank you.